Hello AP Chemistry and welcome to IMFs and phase change. So last little tidbit of the unit. So obviously, again, just to re-emphasize, right, like we've talked about, right, if I separate things, if I break IMFs, that is an endothermic transition, every time I put things back together such that forces of attraction are reestablished, then it's an energy out process, right? That is exothermic, right? Couple of things to note here, right? Note that vaporization is always, doesn't matter what the substance is, right? Vaporization always requires more energy than melting for a given substance. Yes, always. Now, why is that the case, right? That goes back to the definition of what vaporization is versus melting, right? Vaporization is the complete breaking of intermolecular forces such that every particle acts independently, right? Going back to kinetic molecular theory, where the assumption is that there is no force of attraction between gas particles, right? Which means that we've put in so much energy, right, that there is no force of attraction that needs to be considered between those molecules anymore, right? Which then if we go back to that entire gas laws chapter, right, the fact that we can treat every single gas and assume that the ideal gas law applies to all of them is because there are no longer any forces of attraction, right? So they all behave the exact same way, like little tiny point particles, okay? Melting is different, right? And that range is a little bit fuzzy. On average, yes, it does track that the higher the IMF, the higher the melting point, but it's less an obvious thing, right? And two, when we're melting something, right, we're not breaking the IMFs, we are weakening IMFs such that they are no longer in a rigid crystal structure, which varies depending on the substance, the sizes of the molecules, and all sorts of other things. But again, energy in versus energy out, make sure you know those and the definitions of the respective phase changes. Okay, heating curves, we talked about this last year. I told you last year they're important. I don't know how to thoroughly explain how important they are, right? Things to note, right? Heat added. So heat is constantly being added, right? Temperature does not constantly change, right? Because temperature change has to do with what is happening to the heat, right? So here, from A to B, that heat is going towards, right, heating the solid water, right? The water is being heated, increasing in temperature until it reaches its freezing point or melting point. And at that point, all the heat added is now going to weakening the IMFs, yes? Weakening the hydrogen bonding and the dipole-dipole and the LDFs, right? Which is why there's no change in temperature, yes? All that energy is going towards some other purpose at that point, right? And important to note that during the line, both phases exist simultaneously. Yes, we have solid and liquid water simultaneously until we get here where all of it has converted to liquid. And now again, we get a temperature increase because now we're talking about the heating of liquid water, right? And then likewise up here, right? We get to here, and again, all the energy is going into phase change again, and then we're heating our steam. So a couple of points to note, right? This line is shorter than this line because, right, vaporization requires more energy input, right? Energy input is marked on our x-axis, right? Heat added, right? So it makes sense that that line that represents vaporization should be longer because it requires more energy input. Yes? Make sense? Okay. Likewise, if we take a look here, we'll note that this slope is not the same as this slope, right? Because if we think about ice, right, the specific heat of solid water is something along the lines of 2 joules per gram degrees Celsius, right? Liquid water is on the order of 4 joules per gram degrees Celsius, right? Which means, again, more energy, right, per gram to increase temperature, which is evidenced, right, in the shape of that slope. Yeah, does that make sense? Okay. And then obviously if we were tasked with, I don't know, solving for how much energy it takes to go from one temperature to another temperature, let's say to go from -10 degrees Celsius to, say, 125, right? We would just have to add up all the steps, right? Which would mean going from here to here, right? Then going from here to here, and then here to here, and then here to here, and here to here, which is exactly like we did last year. Okay. Moving along, vapor pressure. So note that this is a liquid property, right? So all liquids have an equilibrium vapor pressure, right? So here, this is the only scenario wherein we could really talk about equilibrium vapor pressure. So one, we would have an evacuated flask. We would put our liquid in there, right? And eventually, right, some of those molecules begin to vaporize, right? Until we reach our equilibrium, right? Which is where the rate of molecules entering the gaseous state is equal to the rate of molecules returning, right, such that there's no further net change in pressure. Yes? Does that make sense? And that's what vapor pressure is. So the stronger the IMFs of something, the lower the vapor pressure. Yes? Stronger IMFs, lower vapor pressure. Yes? Because, right, if it has stronger IMFs, then it requires more energy to turn into a vapor, right? It requires more energy to enter the vapor phase, right? And so that makes sense, right? And note that this also ties back to thinking about your gas laws unit, right? As we increase the temperature, right, we increase the vapor pressure necessarily, right? Because obviously, if we increase the temperature, all the molecules have more kinetic energy, therefore more of them are able to escape into the vapor phase, right? Which then is the crux of boiling, right? So if we think about room temp, for example, so let's say we're talking about 25 degrees Celsius, right? Some of the molecules are able to enter the gas phase, right? But we don't get bubbles in our solution, right? Unless, going back to, again, gas laws chapter, right? Some of the dissolved gases, right, can form bubbles and then leave, right? Which is different than the liquid itself forming gaseous bubbles that leave, okay? So here we get the condition of vapor pressure is less than atmospheric pressure, right? So they can't leave. So they're not actively leaving at a significant rate, right? When vapor pressure is equal to atmospheric pressure, because if we think about what boiling means, that means that there has to be a net flow out of whatever beaker, pot, whatever, net flow, right, of the gas out into the atmosphere, right? Which means that it has to be able to push against the force of the atmosphere being applied to it, right? So if that much force is being applied, then the gas being produced has to be able to push against that. Yes, does that make sense? Which is why that's when boiling occurs, is when the vapor pressure is equal to the atmospheric pressure, where vapor pressure, again, the pressure of the gas above the liquid of said substance, okay? Okay, phase diagrams, just really quickly. Note that it just represents the most dense phase is going to be your solid, right? Where most dense means our highest pressures, right? Highest pressures and lowest temperatures, right, are going to be your solids, right? Gases are going to be the opposite, right? Highest temperatures and, again, this being our pressure, so lowest pressures. And liquid will be the stuff that's somewhere in the middle, right? Where the lines represent the phase change between the respective phases, right? This is represents the temperature and pressure, right, of sublimation or deposition, right? If we go over here, right, this is the phase change, the temperature and pressure for vaporization or condensation, right? This would be the temperature and pressure for melting and freezing. Yes, does that make sense, right? One thing to note, right, water is unique in that its line goes back this way because, ding, 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 right, water is unique in that as we increase the pressure on it, right, it actually becomes liquid, right? And that liquid is the most dense phase of water, right? Which is unique to water versus other substances. All right. Thank you for listening. Be good, and I will see you soon. Bye.